So that's the title. As you can get from the title, the idea is to try and get some representation. Shows the name, at least for now. It might still change. Open knowledge graphs to give kind of the perspective that we are trying to create structures that are inspired or resemble in some sense the notions that were introduced in the domain of knowledge graphs. While the goal is basically to create a representation that allows us to consolidate and to explore the information in multiple texts. So that's kind of the title. And this didn't fit in the first slide, but it's kind of ongoing work with quite many collaborators. The first people up to here are from my group, and these are people from Darmstadt and Ross, and Luke and Julian. I guess people know them here. So I'd like to start with the motivation by kind of shedding light on two perspectives on current state of affairs in semantic NLP. And these two, I have a slide for each, so this is just the titles. So one is the fact that typical semantic representations use what I called here pre-specified vocabularies or schemata. And the other is that typically if you want to develop a semantic application and you want to use the NLP pipeline, the semantic NLP pipeline will typically end at the level of single sentences. So let me say a couple of words about each of these. So as you know, typically when people define a semantic representation scheme, they decide what kind of information they would like to encode there, what would be the vocabulary of their schema. Like you may have semantic roles, you may have verb senses, you might link to VerbNet with its verb senses. So part of it is usually defined in the schema itself, and part of it may refer to external resources that also give you some kind of formal representation that people have invented in order, thinking that's the best way to capture semantics of language. And as we all know, vocabularies differ, so one formalism usually has a different kind of formal vocabulary than another. And this kind of raises questions because if they differ, it seems like there's some arbitrariness in choosing what's the best representation to use. If you have 50 relation types, you know, why 50, why not 51, why not 49? And the question is, of course, I mean, people define these schemas of vocabularies because they somehow have under the assumption that this would be in some sense optimal in a specific setting for downstream application development. When you're an application developer, usually you do refer to some of the notions in the vocabulary. And even if you're just going to kind of feed it in a completely kind of black box manner to a machine learning system, then again, you know, is the information encoded in the schema really the optimal one to serve as kind of features or signal for machine learning? So there's some kind of arbitrariness there. And there are some also consequences to this state of affair. One, it's red, yeah, right? Okay. I hope you see it. For me, it's harder to see. Can you see it actually, or? Okay, but I mean, here we are friendly, so I'll just wave my hands. They are long, so fine. Okay. I mean, and a couple consequences. I think one is that it requires expert annotation, and that's always a problem. Because if you think of, take a recent example, AMR Bank replicating some project because you want to enlarge the data, you want to adapt it, to create data for another domain, for another language, it's a huge effort. And also, so that's kind of on the data, on the kind of gold standard generation or training data set generation side. And also on the usage side, I mean, if you're an application developer and you would like to use AMR or MRS or CCG, I mean, you have to learn quite a lot. And I think beyond kind of the difficulties for NLP developers, I'd just like to point also at a general perspective that we know that in general, NLP technology is kind of hard to use. To develop NLP text-based applications that use some NLP technology, usually you have to hire NLP people, right? I mean, unlike like if you want to develop an application over a knowledge graph, then you can take more kind of standard software engineers. So there's kind of a problem that the NLP kind of formalism require quite of specializations. But there have been some exceptions, especially actually coming from the crowds here. So I'll mention them. I'll mention them. Maybe I just want to say, as Luke said, I mean, my kind of endeavor in the previous decade has been about textual entailment. And one of the things that people liked when we introduced it, that it was theory neutral. The textual entailment problem is only phrased in the terms of natural language utterances. You just have to judge something about natural language utterances. You refer to kind of human understanding of language. And people liked it because before that, people were talking about inference mostly within particular semantic theories. And then you really had to be into the semantic theory in order to think of natural language inference. So this is a perspective that we would like also to carry on. So that's one aspect I'd like to talk about and see whether we can do things a bit different. The second aspect of semantic pipeline is the fact that it ends at single sentence. Right, most semantic representations nowadays, and again, next I'll talk about some background. So there are some attempts to go beyond that, but especially with respect to tools that you can download today, it's single sentences. While if you think of it, typically when you access information, I mean, nowadays, if you are interested in information about a particular topic of interest, there are always multiple texts that address your topic. It might be a news clusters about some news events. It might be one of the domains we're working on, educational. Your child is gifted and you're searching Google for gifted children to learn, how to handle a gifted child, and you get 500 documents back. In any scenario, that's the case. You look at products and there are many reviews, etc., etc. And most applications need to deal with these multi-text information. So be it, of course, maybe the most kind of trivial scenario is multi-document summarization. Then that's part of the task definition. You want to somehow consolidate information from 100 reviews of a product. If you get into, I call it kind of slightly complex question answering, suppose you have two relations in a question, even such an if question, right? Where was Trump's wife born? So you have the Trump's wife, so the wife relation, and then you have the born relation. And these might be scattered in two different documents, one that will tell you that Melania is Trump's wife and another that she was born in Slovenia. And you need to consolidate that. KBP, text mining, textual entailment from multiple texts. Often you want to entail something not just from a single sentence, or from even not necessarily from a single document, etc., etc. And what happens today, because semantic pipeline typically gives you representation just for a single sentence, application developers has to do all this kind of consolidation or merging information, any kind of cross-text inference on their own. And if something is related to individual application developers, usually the consequence is that, that development is slow and you don't get so far. I mean, today's NLP technology is not that great in pulling together information from multiple documents. And it seems we'd like to get there in the next step as well. Yes?
Early question here. Where do you see paragraph level comprehension fitting closer to single sentence, or where you're headed?
It might fit in both. I mean, if it's few sentences, there's also already a matter of consolidation. So even if you deal with paragraphs, I would suggest that what I'm going to present now could be useful. Okay, so these are two motivations. We'd like somehow to see whether we can be more theory neutral, vocabulary free, and approach the multi-text level. Okay, so these are the motivations. So the outline would be as follows. First, there's nothing new under the sun. You just compose ideas that were floating around. So I'll talk about some background that's related to our paradigm. Then I'll present our proposal for the open knowledge graphs. And finally, the last part, I'll talk about our kind of flagship application. So having the motivation to be able to address the information in multiple texts, kind of the information which I kind of believe, even independently of the specific formalism, is that what we call interactive text exploration. You get these 100 documents. how you can most effectively communicate their content to a user that under the assumption that on one hand, they won't have time to read all the information, they won't be interested in knowing every detail in these 100 documents. And on the other hand, there's going to be probably something dynamic. I mean, you can't just give them a single multi-document summary. So I'll talk about this paradigm and show an initial prototype that we have developed. So these are the two kind of main contribution parts of the talk. And just kind of as framing the talk, it's not a talk about a particular algorithm, it's more the talk, so I won't be describing any algorithms today. It's more like on a long-term roadmap where also is kind of a disclaimer, we are now at initial stages of setting it up, even though it just took us, I guess, 2-3 years just to get into this roadmap. So I am summarizing, presenting the outcome of some effort, okay? So that's the outline. So let's start. Okay, so semantic representation. Let's have a quick look of what's out there already. More recently, kind of graph-based formalisms or representations became popular. Maybe the most popular one in the sense, if you count ACL papers that relate to it, is nowadays AMR. It's not that it's being used that broadly right now downstream, but people work on that. Is AMR. It's an abstract representation. So graph nodes kind of refer to abstract concepts, not to the actual natural language elements. So it can be, sense 0, 1 of want or frame or believe in verbnet. And edges represent, so it's abstract elements, and edges represent relations or some predications between these elements. You can see, since it refers to abstract elements, coreferences get collapsed. So you have, boy and him both refer to the boy. So it's the same abstract entity. So kind of there's one node for each coreference chain. It relies on propagand frames. It refers to this. It does specify dozens of relation types. You can see various types. I mean, here it's just the prop bank ones, but you'll see in a minute additional relations. And the structure is not directly aligned with the original sentence structure. So in that sense, it's a bit harder to generate or regenerate sentences. Now, there is current ongoing unpublished yet work on multi-sentence AMR that does try to go beyond the single sentence level. And maybe the main idea I'd like to point at here is that indeed, we have two individual graphs, and now we have a conjoined one. And the main thing is that we, again, as in single sentence, we can collapse coreferences. So he and boy, again, get to the same node, and then the coreference kind of bridge, actually, the information. This is work that was done. As you'll see, we use the similar idea of collapsing nodes based on coreference. It was kind of developed in parallel. So we see this collapsing, and you can also see that it may capture implicit relationships, right? There's no syntax saying that the boy arrived to California, but this would be an implicit argument. Identifying implicit arguments is a known task in NLP. There's been a Semeval benchmark about it and a few papers, not a rich line, but there has been some line. We also had a paper related to this a few years ago. So we'd like to capture those as well, because from a semantic perspective, whether the syntax expressed it or that was kind of trivially implied for any reader, we would like to know that the boy arrived to California. Okay, so we want these as well. So that's AMR. Another example for a representation is MRS and semantic dependency graphs derived from MRS. Again, there was a semantic Semeval task about that. Here, I just want to know, so it's kind of similar graph flavor of lexical elements or sentence elements and edges relating them. But this is a bilexical graph, so the elements here are actually lexical items. So it ties more closely to the lexical elements in the sentence. Okay? Most importantly, to the content words of the sentence. Yes. Sorry?
What does MRS stand for?
Minimal recursion semantics. Emily Bender and Kopstake, they're formalism. So these are two examples from kind of more the semantic representations literature. And another kind of, again, very thin couple works, line of research that had similar flavor was within multi-document summarization. In particular, from a couple just from last year, state-of-the-art performance on abstractive multi-document summarization on popular DAC data sets was achieved by a method that took this event semantic link networks. That's a less known formalism. It was developed a bit in other communities. You see, it's from kind of more like semantic web and these kind of communities, but it's again have a similar flavor. You'll see an example in a minute. And for the purpose of multi-document summarization, it was extended for the multi-text setting. The next slide will illustrate it. And it achieved state-of-the-art performance. And it seems that kind of these merged multi-sentence graphs kind of lend themselves to multi-document, to abstractive multi-document summarization. And there was a similar work also based on AMR. Again, quite two similar works that followed recent works that follow this perspective. And just to give an illustration, these are these event semantic link networks graphs. You can see also kind of a quite complex vocabulary of relation types. But the idea is that if you have these two for two sentences, two original sentences here, you again consolidate on coreferences. So this is the this from here and this from here. They get collapsed, edges from both sentences merged. In this step, it's already after reduction for the summary purposes. So first, you just collapse the two, and then you decide what's salient, and eventually you generate a sentence kind of naturally from here, right? You have here this who was a lawyer, so was a co-founder of a company, so you generate this who was a lawyer and the co-founder of the blah, blah, okay? So it's very natural to generate kind of abstractive summaries, relatively natural from these graphs. So you can see kind of a thread that builds graph structures, merges them based on coreference, and then it seems to be quite lending itself for summarization. And of course, in order to do that, you need to find all these coreferences, and there's been work, again, somewhat thin thread of work. I mean, there's been a lot of work on coreference, but on cross-document coreference, most work has been just about named entities. Here to do these graphs, you just have to co-refer everything, so including events, including common nouns. Okay, hasn't been that much work, but there have been some on predicate argument alignment, ECB plus, ECB plus, EECB. There are some variations. It's a corpus of cross-document event and entity coreference. Little work, but basically, there has been some work trying to identify these coreferences. Okay, so there's some directions in it as well. So this is kind of where the community has gone, and I'm actually pulling out threads that are quite thin. It's not works that are in the heart of NLP today, except maybe for AMR, but there has been some work, so at least the problems have been established. So that's kind of the typical kind of type of representations. Now, there has been another trend that we are going to follow about vocabulary-free representations. While most work does define schemata with special vocabularies for senses and relation types, etc., there has been some work which we try to follow. We are following the spirit of this work. So I'd like to mention two lines of work. One is OpenIE that Oren started, right, where you take a sentence and kind of extract the core propositions in these statements, usually around each predicate. So we seek two propositions. And kind of the philosophy here, right, there's no roles here, there's no vocabulary, just some concatenation of natural language elements. The only distinction is that one of them is designated as a predicate and the rest are as arguments. And you kind of understand, but you still can read this. And the kind of assumption is that, yeah, at least in text-to-text application, eventually if you present this information, it's clear. When we read these propositions, we understand what the relation is between the arrived and any. We understand that any is the agent, even though we don't know to call it an agent, we understand that Danny, is a performed that derive, and this was the destination, and this was the purpose, right? We could understand that just as naive language speakers. So kind of the semantics are coming from the natural language expressions involved in the presentation, okay? So that's the basic idea. What we see we don't have here, we don't have at all a kind of a denotation of the roles, right? Nothing here says that this is the location and this is the purpose, but you kind of get that from the content of the words. More recently, QA-SRL, the reference will be in the next slide, suggested that maybe we can also capture in natural language terms also the roles between predicates and arguments. So basically, as kind of background, right, predicate argument structure is often specified if you read the prop bank kind of introduction. When people talk about semantic role labeling in general, they always say that what is a role? A role is kind of corresponds to some question that the argument answers. So, what is Obama? It's the answer to who was born somewhere. That would be the agent role. And what is Hawaii? The answer to the question, where was someone born? That would be the location role. Okay? That's what typically kind of repositories that use an explicit vocabulary, predefined vocabulary of roles, the approach they would use. And the QA-SRL work by Luheng He and Luke suggested, okay, let's follow this idea that roles actually are the questions that the argument answer, and let's collect these questions. So like if so what they did an annotation effort where they marked the predicates and asked people to phrase questions and answers related to the predicates. And then the crowdsource workers would put up questions like, who was born somewhere? Obama. Where was someone born? Hawaii. And then this question-answer pair could actually serve as the role of the argument. So we will have a specification of the roles, but again, in natural language terms. There's no predefined vocabulary. Whatever the Turkers came up with, that's what they've put. Okay? So these are the kind of two works that use natural language terms to describe semantics, avoiding a specification of a concrete vocabulary of relation types and senses, etc., etc. And this is the flavor that we are going to follow. Okay? And lastly, I would just like to give a perspective of where we are kind of heading. I mean, not in the natural language domain, but rather in knowledge representation, semantic web, etc. People came up, and semantic networks of the 80s of the previous century, starting then, people came up with the notion that in order to represent a large amount of information, consolidated information about some domain, it may be useful to put up this kind of structure, which a little bit resemble the graphs I've shown before, right? Where the nodes are the elements in the domain that you want to represent, and edges represent minimal relationships or predications, statements that about these entities, like this one states that this is the date of birth of Obama. It may be true or false, right? Each such edge corresponds to one statement that can be attributed a truth value, right? And it just try to assert what is true. And these knowledge graphs, as you know, are very successful. I mean, from Google don't publish much about their knowledge graph, but I know it's just getting more and more used and more strategic all the time. So these kind of structures seem to be very useful for many downstream applications. So the question, kind of the perspective, and these are the knowledge graphs. I mean, one thing though a couple perspectives. So this is the appeal, but on the other hand, one thing to note about the knowledge graphs that again, right, they have all these vocabularies, and you have to define the vocabulary of the semantic information that you want to encode, and therefore typically they represent only a small part of the information. Knowledge graphs encode, a tiny fraction of the information that's out there in textual information. So they are good for kind of pre-specified, curated knowledge, but they don't address the issue of how can we approach kind of the vast amount of information that's available in texts. Okay. So based on this background, you can define our goal as finding a way to represent consolidated unbounded information that's coming from text on the one hand, and second, as being the last part of the talk, how can we effectively communicate it? But the approach we are taking is in order to address unbounded information in a more easily kind of crowdsourceable way, we take the open natural language-based approach in the flavor of OpenAI and QA-SRL. And we would like to allow exploration at the level of these statements that we are going to encode. Okay, so that's just the goal. So let's start and see how we are about to develop kind of our approach. I'll illustrate our approach using these 4 sentences. So these are 4 sentences, particularly taken from a cluster in a multi-document summarization setting. So this was a cluster of documents about the evolution of Starbucks. And here we can see 4 sentences, each taken from a different document. And all of them refer to the same event of the same acquisition of this passcode chain. Each of them, so there's some overlap, but also some complementary information in the different sentences. So first, we would like to come up with a graph structure like that resembles the graph structures that we've seen before, but on the other hand is open in the sense of QA-SRL. So what do we have here? We see that the nodes correspond to terms or to content words, while we assume that each node corresponds to some real-world element, as in a knowledge graph, that is referred to by the sentence, okay, like the Pasqua coffee. And it may also be, an element may be also an event, right? It can be an entity, a concept, or an event. We would like to consolidate co-referring elements, as in other formalisms, like in AMR, because the eats and the Starbucks refer to the same element in the world. We just would like to have them be represented in the same node. And notice there's also no distinction between predicate nodes and entity nodes. We actually had a predecessor of this formalism when I was presenting kind of earlier versions of this approach a year ago. The presentation was different. We published, by the way, the previous version in a workshop this year, LSD, Lexical Semantics, this Lexical Sentential Discourse Semantics workshop that took place at last EACL in April. And there we did have a representation that did distinguish predicates and arguments. And one of our findings was, that's an interesting finding, I think, that one of the major source of disagreements, one of the major sources for disagreement of annotators, it was trained annotators, was whether a node is a predicate or an entity. I mean, think of a word like, yeah, I see people, I saw you kind of trying to think of an example. But for instance, hurricane. Is hurricane a predicate or an entity? It's not completely clear, right? A hurricane in St. Louis, okay? Storm may be easier, right? When I say hurricane, it's kind of, initially you think it's an entity, but if I say storm, okay, that's normalization. Maybe it's actually a predicate. So the borderline is not clear. And we figured out that actually in this kind of representation, similar to knowledge graphs, you don't really have to distinguish the two. You may, later on for generation, you might know that this is a verb, or you might even know that in the easy cases, keep track whether some things are considered in NLP as predicates or not for text generation purposes. But from the perspective of information representation, you actually found that we think that we don't need actually to distinguish the two nodes types. And the nice property we found that when our annotators disagreed about whether something is an entity or a predicate, regardless of the decision in this kind of reduced formalism, whether you thought initially that it's a predicate or an entity, you ended up having the same structure. So avoiding the distinction in the final structure actually helps kind of circumventing disagreements. Yes, I see that. I said a controversial statement, so.
Without getting segued too much, do people also disagree about the arity?
I think that was, I have to pull out, I mean, it's in the workshop paper. We have like a table with all types of disagreements. I think on the arity there was lower disagreement, but occasionally that happens as well. But arity, I mean, you know, arity would be everything that should be, in a sense, an argument of acquired should be linked to acquired. So if you miss something that does have a relationship with the acquisition event, then you reach disagreement.
Just think of entities as predicates with lower arities.
Maybe let's not segue too much. Yeah.
There's some concept of like arc 1, arc 2 here. How would you know that Starbucks acquired Pasco Coffee as opposed to Pasco Coffee acquired?
Okay, I'll get to that. I'm only the nose now. Let me get to the edges. Okay. So okay, let's move on. So I was just thinking that this one is kind of an interesting perspective to give because it's, I mean, it took us some kind of rendezvous in order to get there. Okay, now about the edges. So an edge basically represents a minimal statement, as in similar to other formalism, that connects to two elements. It can be as between a predicate and its argument, but it can also be like between two nouns, like the Starbucks network. So it implies a relationship between, you know, this network belongs to Starbucks. This kind of, you can have something like passenger plane. So again, passenger plane versus maybe jet plane. So this relates a bit, I just mentioned it, to the whole issue of implicit relationships in noun compounds. But the point is that each such edge does reflect a statement that could be asserted based on the question. It could be assigned a truth value, and based on the sentence, is claimed to be true. True or false, I mean, it can be asserted based on the sentence, yes?
Does that mean edges have direction?
It's a good question. Let's see, let me, okay, let me first explain the label and then I get back. It's a tricky question. We've been discussing it quite a lot. So what is the label? The label is somehow supposed to reflect the assertion that relates the two element nodes, okay? And the label is basically a question-answer pair. So here I just this is just like a summary. The actual label would be the question-answer pair as in the QA-SRL paradigm. So like what was acquired? Pasqua coffee, where the acquired would point to this node, and the Pasqua coffee would point at that node. So it's kind of a natural language template in this form of a question-answer pair, which have designated slots to denote the two end nodes of the edge. And this ties to your question. So from the sense of a directed versus non-directed graph, we can actually refer to this as a non-directed graph because there's kind of no consistent meaning as in dependency trees, let's say, of a particular direction. Because also you could argue, I mean, you could see some edge that in one sentence, you know, one node will be the head and the other the modifiers, and another sentence where it's kind of the construction is reversed. But so from a graph perspective, you can think of it as a non-directed graph, but the labels are non-symmetric. Right? The label does say that this is the acquired node, this is like the verb node, right? What was V1? What was acquired, V2, Pasqua coffee, okay? So the template is non-symmetric. There are designated positions for the nodes. So that's, yes. So the label is kind of, yeah. So I mean, from global graph perspective, there's no meaning for directionality, but the label, yeah, is kind of, you could think of it as direction. It's non-symmetric. It's not that you cannot say it's in this direction or in that direction. There's no concrete direction, but it's non-symmetric. I think that would be. It's a strange animal. We don't want to get into all the discussions. We had it in our lab, so let's leave it for offline. Yeah. I'll be happy to discuss it if you have any insights, but let's leave it off.
This is a silly question, but like, why is Starbucks a who and Pasca coffee what? Like, do you always just make the agent a who? Like,
No. I'm saying this is just a shorthand to hint at the actual QA-SRL type of question. So you would expect that here the annotator would put a question like who acquired something. Yeah. While here the annotator would put a question like what was acquired? Pasqua coffee. Okay. So this is just like a hint at the fully phrased question. Okay. Okay. And of course, when we follow QA-SRL, notice that, I mean, different annotators might give different questions. So actually, if we use multiple annotators, you may have actually a set of questions as a label, where you assume that all these set of questions are all kind of paraphrases of each other, as much as annotators are consistent. Okay. Okay. So this is the representation for a single sentence. Okay. So basically, just summing up, it's kind of a graph in the style of graph-based representations, but plugging in the kind of QA-SRL methodology to have a vocabulary-free type of graphs where the semantics come from natural language expressions that are attached to these graphs on the nodes and on the edges. Okay. Now we would like to consolidate multiple texts. So now we have 4 graphs for the 4 sentences we've seen before. Okay. And we would like to somehow merge them or consolidate them. And here we will use the approach we've seen already before, like in multi-sentence AMR or in these works on summarization. So we need to identify the coreferences, Starbucks, they. They all refer to the same element. We would like to have eventually a single node for all of them. And when I'm saying that, or similarly, we can have nodes that correspond to events, and in this case we would need to use event coreference technology. But again, once we've identified that these nodes all these nodes correspond to the same acquisition or purchase event, we would like to have them as a single node. Okay? And at this point, I would like to, when I'm pointing at the references, I would like to kind of point out one interesting observation. Right? So the perspective here, I mean, the representations I'm coming up with, tries to remain, at least as a starting point, completely at the language domain. Right? All these approaches like OpenIE, QA-SRL, textual entailment, they try to phrase our representations by sticking completely to the language level. Right? On the other hand, what I would really like from a semantic information access perspective, we would like to actually correspond to elements in the real world, right? I mean, the user of any kind of semantic application isn't really interested in how exactly the acquisition was phrased. They think of Starbucks as an entity in the world, of Pasqua as an entity in the world, and of the acquisition relationship as some event that related these two elements, right? So we'd somehow like to represent elements in the real information in the real world, but we would like to be tied just to the language level. Now, what is the element in kind of language processing that ties between the text and the world, while avoiding, I mean, of course, you can go to Wikipedia or to Wikidata or any kind of knowledge base, and that is supposed to formally represent elements in the real world, but we want to avoid it. So if we just want to use textual level but refer to the actual external world, the element that bridges us, the task or kind of the information that bridges us from the text to the real world is coreference. Because what is coreference? When would you say that Starbucks and they should corefer? That's the definition of coreference, right? If they both refer to the same entity in the world. When would you say that the purchase and the bought you should link them in event coreference if they both co-refer to the same activity or event in the real world? So actually, without much paying attention to that, coreference is the task that bridges the lexical element, the purely textual element, to something unknown for which we don't have another representation in the real world. That's why actually a coreference chain is a textual representation of a real world element. Okay, and that's what we'd like to get in our graphs. So coreference does the bridging. Okay. Yeah.
Quick question here. You mentioned event coreference, and I'm kind of wondering if there's a chicken egg problem here. If I would like to do event coreference based on these graphs, but then I'm doing the assuming they've already done the event coref. So what's the relationship there? How should I think about it?
You could first do each sentence alone, and then you try to apply some coreference technology, both for entities and events. Okay? I mean, that's exactly what they, by the way, are doing in this ECB data set, where it's a data set of annotated sentences. In the gold standard, you have coreference links both for events and the entities. And you're trying to develop algorithms that will do that. Okay? And indeed, some algorithms, nice algorithms, actually do it. I mean, some do it in a pipeline. some do it actually globally and simultaneously try to, there is a nice, it's not state of the art, but the previous paper from Stanford, I forgot his first author, but Juravsky is one of the authors, that do it jointly. And in fact, the algorithm, again, doesn't really distinguish whether a certain coreference chain is of entities or predicates. They just try to resolve all coreference chains together. So that's also kind of raises interesting, I mean, doing joint kind of resolution of entities and events is kind of a nice problem that whose solution would benefit this framework. Okay, so we figured out that each coreference chain is a single, refers to a single real-world element. So now we'd like to collapse the nodes, and all the acquired nodes collapsed here, all the Starbucks nodes collapsed here, etc. And we have one graph that basically summarizes the information in the original sentences. So every kind of statement that's included in one of the original sentences appears here, while redundancy gets collapsed. So every statement appears only once. And as you can see, this kind of structure very much resembles the structure of a knowledge graph, right? Each node refers to a real-world element, and edges reflect minimal statements relating these elements. You can also see, once we collapse, we keep track of where did this node come from. So we know, for instance, that this occurred in all 4 sentences. So, for illustration here, we marked it as bold. So you can immediately see what are the more kind of prominent, more salient elements in the graph based on the original text. So let's just see, what have we represented here? So the graph, we view these graphs basically as kind of a compact representation of all the statements, all the verbatim statements that could be expressed jointly by the text. And you could think of express as being entailed. And I said kind of verbatim, so the graph, right, as we've seen here in the graph, we only have lexical elements from the original words. We didn't put company anywhere here, okay? Because we really think that kind of from an architecture design, open-ended lexical inferences should be handled by another layer, okay? If we'd like to put company or fruit for apple, etc., it's quite open-ended. So the goal of the graph is to capture the information in the terms that did occur in the original sentences. And the kind of inference that's already encoded in the graph is based on these mergings, these consolidations of coreferences, right? If we had a sentence, a plane from Russia, doing something, and in another place it says a Syrian jet, we can infer that this was a jet from Russia, right? Because we know the jet and plane. If we identify the coreference between jet and plane, we can combine the information and infer that we are talking about a jet from Russia. Okay, we had only information about a plane for Russia, and the jet we knew was Syrian. But once we've done the coreference, we can know also that that plane from Russia, we infer that it's not just a plane, it's a jet. It's a typical kind of coreference-based substitution that people often do in applications. And the other kind of inference that coreference allows us is to merge elements, right? We kind of merge everything we knew about this flying event from different sentences. So that's basically the meaning of the graph, okay? It represents all the kind of minimal statements that could be asserted jointly based on the coreferences by reading the entire set of sentences. And what I'd like to suggest is actually that this is kind of a sensible requirement, right? Because I was kind of showing graphs. It all looks very natural and neat. But we'd like, okay, but what would be a requirement? If someone were to invent somewhat different representation, what should be a kind of a core requirement for these representations? And I'd like to suggest here that if we're talking about an open representation that doesn't want to commit to some pre-specified vocabulary, a sensible requirement would be, okay, your representation should capture, it's open, so it should be a natural language term, but it should capture all the natural language statements that could be asserted based on the texts being read jointly. Okay, so that's a proposal. And you can think of that you can test your representation by seeing whether, like if I'd ask people to phrase verbatim statements based on the text, does my representation cover all of them? Like completeness requirement, and if I can read out some statement from my graph, is it sound? Is it indeed a statement that could be supported by these texts? Okay. So that's kind of what the graph suggests. And now I just like to, I just very quickly, for the sake of time, I'll just mention another one. Once we have so many statements represented, obviously, many of them will be redundant, right? Like the jet arrive, the plane arrive, there's some redundancy here. So I'm suggesting that also another suitable requirement, in order to answer it, I'm going to extend with one more layer of the graph, the last layer of the graph. Another requirement would be redundancy modeling, because the graph encodes all the statements conveyed by the text. There is a lot of redundancy between these alternative statements. We'd like to model the redundancy. And you could somehow think, what does it mean to model redundancy? I could phrase the task as by supporting incremental communication of the information. So if I already, for instance, told you that a plane arrived from Russia, and now I figured out it's a jet, I may tell you now, hey, I have an update. It's actually a jet that arrived from Russia. Jet is more, gives you some more information. But if I already told you that the jet arrived from Russia, and now I have a sentence that the plane arrived from Russia, there's nothing new I should tell you, right? Because plane is already entailed or subsumed by jet. So this is kind of a way to require the ability to model the information redundancy between elements. And it's very natural because, for instance, if you want to communicate answers or summaries, you don't want to provide information that has already been communicated. So this could be kind of a way to phrase a requirement of what it means to model information redundancies.
Does the completeness part cover the example you gave earlier about a boy ran off to San Francisco and arrived yesterday?
The arrived yesterday is more like of an implicit relation, right? And you'd like to cover that as well, because humans would tell you that they got it from reading the two sentences.
So
okay.
that is part of it.
That would be part of the completeness, yeah. Okay? So how can we model that? We would like to model it from an entailment perspective. And notice, for instance, you have here two sentences. Turkish military intercepts jet, or plane grounded by Turkey. Which one is more specific? The first one, right? And the first one doesn't entail the second, right? So notice that this one is more informative than that one. So if, for instance, if we already communicated the first one, there's no need to communicate the second. But vice versa, if you only communicate the second and later you have more information, it makes sense to communicate the first. And notice, so this is the more informative aspect. And notice there's also another kind of relevant interplay here, that while the second sentence is more general, it would have more support in the original tweets or in the original sentences. Suppose, remember this boldness, this kind of frequency. If I've seen these two sentences, then this information, suppose I've seen these two sentences in the original text, then the information here have only one point of support, right? Only one sentence supporting it. While the information conveyed here is actually supported by two sentences. In a sense, it's more salient or more certain, right? You see why? Because this sentence also implies this one. That's why the information conveyed in the second sentence actually has two supporting sentences, while the first one has only one. So we have here an interplay between, as information becomes more general, it conveys less information, but it typically has higher support. Yes, you wanted to ask something?
Yeah. How does your system know that we're talking about the same plane and same event even?
It does event and entity coreference properly. Okay, of course. I mean, we have to. I mean, there are already some. I mean, one of the challenges, to make these frameworks useful is, I mean, we have to take seriously cross-document coreference and get improved with these problems. I just like to point one element, even though to get everything right, it's we have tough NLP challenges that are on the NLP roadmap anyhow, right? Just haven't gotten there yet. But I want to mention that when you're talking about multi-text consolidation, suppose I had 100 documents, if I even covered half of the information, I already covered a lot, and maybe in just 50% recall, you can get with the easier cases, okay? Because, and basically, because it was in the same date, it involved the same players, Okay, there was quite high matching of predicate argument structures. So, I mean, people in the reasonable cases, people do. I mean, you can imagine this being got right. Okay. So what we suggest is to model this in entailment perspectives, right? Because basically this sentence is entailed by this one. So, and we suggest that to model it more specifically at the term level. I won't go through this. I'll just show the final direction. What we do is within each coreference chain, right? I mean, jet and plane all refer to the same element. Grounded, intercepted refer to the same event, etc. So what we do, we've seen before that in each node, we have a bunch of terms, right? All the different terms used within the coreference chain to refer to that element. Like we had acquired and purchased, or we had stores and outlets. So what we do as an additional layer in our annotation, within each coreference cluster, we draw a small entailment graph that tells us which terms are more specific, which terms are more informative, which terms entails other. And then we can start doing these types of entailment between sentences in a compositional way. Okay, so I don't want to spend more time on that, but the general idea is that, just to sum up, the semantics, if you like, of the graph is a set of all statements that are expressed jointly by the text. And we would like also to model, since there are there's a lot of redundancies there, we would like to model the information containment between these statements, and we do that through entailments, through lexical entailments. Okay, there are some additional issues. I'll skip those, but I mean, there are subtleties that have to be addressed. I just skip those issues. Okay. What we've done so far, we have created an initial expert data set of news tweets, okay? And we are in ongoing development of an automated baseline system. And the other effort we are doing now, together with Luke and Julian, his student, is to try and derive these graphs from a QA-SRL type crowdsourcing effort. So the idea is to take the original QA-SRL that was restricted to verb, extend it to all words, to try and identify through question answers all semantic relationships between word pairs in the sentence. So like Nomilan, when did the landslide occur? On Thursday. What village is located in China, right? This village, etc. So these are nominal relationships or adjectival relationships. What was rapid, etc. So the crowdsourcing has to be extended not to address only verbs, but any kind of word pair. And the idea is what Gabi, my student, is working on, and we are now joining forces in all these steps, is to try and from this noisy set of question-answer pairs that relate all words to all words, I mean all the words that are related to each other, and on average you get like over 50 question-answer pairs per sentence, to derive kind of the skeleton graph structure that you are after. And this is just an example of how it was done for the first sentence in the Pen-Tree Bank, which is part of the annotated data. Okay, so this is the general idea. We cannot ask people to directly annotate the graph structure. That's kind of too involved. But from the individual, just one question-answer pair at a time, give a question-answer that relates these two words, we get a noisy set of question-answer pairs, and from that we kind of try to distill kind of a skeletal graph structure that corresponds to the actual relationships in the graph. And we are actually quite optimistic. We are staying here. I'm here this week in order, and Gabi, my student, as well, because we are going to spend time this week to see how we proceed with that. But generally speaking, we optimistically believe that in several months, we'll have, or in half a year, we'll have, or in X month, we'll have a large-scale data set of these graphs. So these are the graphs. I think I'll have to skip the other side. I see Oren picking at his watch. These kind of talks are always, with all the questions, always take a bit longer. So basically, from kind of what do we do with it, basically, I just want to point at two answers. One is, as I said at the beginning, the next step in all semantic applications would require us to handle multiple texts. So what we would like to envision here is once we have a corpus, to develop a pipeline, etc. So again, in a Y time frame, we would like to add to the NLP pipeline a tool, kind of a multi-text semantic parser that can get 100 documents and give you the graph, kind of the knowledge graph describing these 100 documents that could be, we believe, could be very valuable for basically any kind of multi-text semantic application. Beyond that, as our own kind of flagship effort or application, we would like to develop an approach that improves, that allows you to explore, to explore these 100 documents. So you've given me 100 documents on a topic of interest. How can I build these graphs and communicate these contexts effectively to a user? Current technology is mostly multi-document summarization, but that gives me just one static summary. And OK, I'll read the summary, but then if I want some more information, what can I do today? I have now to go and read the text. We would somehow like to have a more interactive mechanism that will be dynamic and just skip those, but just to give a sense, this is a set of over 100 tweets on Sandy, Hurricane Sandy. We'd like something that would first allow you to show an initial abstractive summary generated from the graph. So there is a graph for these 111 tweets. From that, these sentences are not original tweets. They are abstractive summary sentences generated from salient, from bold notes in the graph. If I would click on Sandy, I might see all the Coreference terms, right? All other terms used to refer to it, like that, it's Frankenstorm, Superstorm. I get some more information. I may want to point at more, unfold more sentences and see what happened in between. Or I may want to eventually go to the tweets, and there are many more ideas. It just gives you the flavor that once you have the graph, I mean, imagine a knowledge graph, I think everyone can start imagining an interactive application that, based on abstractive summarization of selected parts of the graph, can help the user explore the content of the graph, which meaning exploring the original content of all these 100 documents. So that's the direction where we want to go, and I actually believe that from information access perspective, was not the focus of this talk, but from information access perspective, I mean, we've been stuck with a flat result list for probably over 30 years now, and all the kind of visualization effects when you show nodes and graphs and things are moving, those don't really fall away. I believe that the approach should be based on eventually communicating small statements, short statements, abstractive statements to the user and allowing to explore the information space. So that's about it. We've done some user studies, small one, 6 users, but people like it basically. And as I said, we'd like to collect data set, build the technology for all what we've done. So that's it basically. That's what we were talking about. And I don't know if there's time to take additional questions, but